Hi, I'm Mark, and this video is a walkthrough of 2019 AP Physics E Mechanics Free Response Question 1 from Set 1. There were two sets released. There may have been other sets, additional sets that were used, but we got these two sets released. So we know that there were these out there and that students may have had different questions in the same classroom. I'm going to go through this at a moderate pace. This is intended for teachers new to Physics E or anybody who's really unfamiliar with the question. It's not too dissimilar from the pace I would go through it with my students. I would say it might take 45 minutes to go through a problem like this with my students. Okay, so the first part of the question says, in an experiment, students used video analysis to track the motion of an object following vertically through a fluid in a glass cylinder. We get a diagram above of the cylinder with some sort of irregular object and a hand placing it at the top of the fluid. It's resting on a table. The object of mass m equals 12 grams is released from rest at the top of the column of fluid as shown above. The data for the speed v of the falling object as a function of time t are graphed on the grid below. The dashed curve represents the best fit chosen by the students for these data. Okay, so this is actually a fairly typical question, although there's some atypical things about it. Let's just outline what's typical and not typical. So typical, this is going to involve graph, kinematics, forces, in particular drag, with calculus. That's a fairly frequent occurrence, although not necessarily obvious in the free response, or not seen in the free response every year. Okay, atypical. The setup is a little atypical. Fluids are not a subject in AP Physics E Mechanics, so seeing a fluid, a liquid question is a little bit unusual, although they've certainly had lots of questions about air resistance, which is also a fluid. And then the other thing that I would say is atypical is that 9 out of the 15 points are largely, in my opinion, conceptual questions. They're based in mathematics, but they are not calculation, algebraic manipulation questions. Okay. So let's go forward and look at the first part of the question. Part 1 of A says, does the speed of the object increase, decrease, or remain the same? Well, we just looked at the graph, and you saw that the graph was a graph of v versus t, and it was going upwards. The value of v was increasing over time, so we can just select increase. That's pretty easy. Typically, questions start off with an easy part. There's no justification required. You just check increase. The second part says, in a brief statement, describe the direction of the object's acceleration and how the magnitude of this acceleration changed as the object fell. Well, the graph, the best fit was concave down. So A is down because the object was moving down. We don't really need a justification, so I won't write one because it doesn't ask for one. And the magnitude of A decreases because the graph was concave down. Again, we don't need a justification. It's very typical for them to ask for a brief justification, but they didn't on this part. And then in part 3, it says, calculate an approximate value for the magnitude of the acceleration of the object at t equals 2 seconds. Well, let's look at that. So I'm going to go back to the graph. They actually want students to put a tangent line on this graph on their paper and calculate the slope. So I'll do that. Okay, so I went ahead and drew my tangent line on the graph, and then I picked 2 points that I could use to calculate the slope of the graph. Those points are where the tangent line goes through the grid intersections. That's how you want to coach your students to do this. And they should take a straight edge to the exam so they can get a nice tangent line easily. This is not an atypical question. I won't go ahead and calculate from my values because we don't need to take the time to do that, but I would just mention that from the scoring guideline, they're looking for a value of about 2 and 22 hundredths meters a second squared. It does say from the tangent line. So if a student's draw a decent tangent line, doesn't have to be perfect, they get a value that matches their tangent line, they should get those points. I'm going to erase this and let's just go forward. Okay, so in the next part, part B, is where we really start doing the mathematical part and using our calculus. It says the students use the equation v equals a times the quantity 1 minus e to the negative bt power to model the speed of the falling object and find the best fit coefficients to be a equals 1 and 1800 meters a second and b equals 5 hertz. Use the above equation to 1, derive an expression for the magnitude of the vertical displacement y as a function of t of the falling object as a function of time t. So what do they want us to do there? Well, it does say vertical displacement. So vertical displacement is delta y. That equals the integral of the velocity as a function of time with respect to time. Since it's delta y, we need an initial value and a final value, so that implies that we need to put in bounds. The logical bounds for time would be t equals 0, and then some later time t, since we're not given any numbers. This is a little bit confusing. Look at all the t's I've got there. I've got 5 t's, and it's not clear what is what. So this t on the right here, this represents some value of time on a stopwatch, and this t on the left here, this represents a variable. So what the College Board has been doing lately to make this a little cleaner looking is to give a prime. So anything that's that represents a variable gets a prime. The t that represents a specific value does not get the prime. So I want to integrate this function, and let's write that out from t prime equals 0 to t prime equals that later time t, and then 1 and 1800ths minus 1 and 1800ths e to the negative 5t. Give it a prime with respect to dt prime. Now at this point, let's just do a quick little bit of planning. Your students may do this unconsciously if they are really good at calculus, or they may have to think if they're calculus learners, or even look it up in the AP equation table. But this is just a constant, so we can use the polynomial rule or power rule, the integral of x to the n dx equals 1 over n x to the n plus 1 plus some constant, which we don't need to worry about here because our bounds will take care of the constants, the initial values. So let's see. This is 1.18. It's actually, with respect to t prime, well, it's t prime to the 0 power, right? So it's going to be, that's going to lead us to have 1.18 over 0 plus 1 is 1 times t to the 1 to the 0 plus 1 power. Pardon me, t prime to the 0 plus 1 power. So that'll just be 1.18 t prime. Okay, so we figured out what to do with this first part. We're just going to use that power rule antiderivative to get the value. The second part would be the integral of e to the bx dx, and that is just going to equal 1 over b e to the bx plus some c. Again, don't need to worry about the constant. We've got constant initial value, sorry. We've got our bounds, so that'll take care of that. So this is just going to be negative 1/5 times this whole expression right here. So now I've done my planning, I know what to do, so I'm going to erase my, well, I could just come over here. We don't need to erase it. Just write it out and find an answer. So now we know what to do. Delta y must equal, I won't rewrite all this just to save time. must equal the upper bounds part minus the lower bounds. So we said that will be 1.18 t prime of 0 plus 1, so that would just be 1.18 t minus 1 over negative 5, negative 1/5, times 1 and 1800ths e to the negative 5 t, not t prime, because we're putting in the value. I started to say t prime, putting the actual value because we're evaluating the function. All that is minus, okay, well our lower bounds is 0, so this part tells us that we'll have a 0 because we're putting in 0 for t prime, so that'll be 0. And then again minus negative 1/5 times 1.18 times e to the negative 5 times 0. Aha! Well, anything to the 0 power is just 1. So this whole thing is just 1/5 times 1.18. And it's subtracted. It becomes positive because we have minus and negative, and there's a third negative, so it's going to be subtracted. So our answer is going to be delta y equals 1 and 1800ths t minus, what is that? That is 0. Remember, it's positive because it's minus and negative. 0.236, 236 thousandths e to the negative 5t minus 0 minus, well, that will just be the same thing, same value, 236 thousandths minus 236 thousandths, because this part becomes 1. And that's our answer. Remember what we were doing here was, this is evaluating with the upper bounds, and this is evaluating with the lower bounds. So now our answer is this long thing. I think that you could probably get the points with just leaving it A and B, but I like to put the numbers in for some reason. Okay, let's go on to the next part. So the next part says, is B2. It says derive an expression for the magnitude of the net force F as a function of t exerted on the object as it falls through the fluid as a function of time t. Okay, well, that's going to involve Newton's second law. A equals F net, because they talk about the net force over m. We know the mass, that was 12 grams. We don't have acceleration. We're looking for F net as a function of time. So if we have v as a function of time, then the time derivative of v as a function of time, well, that is going to equal, let's clean this up, that is going to equal A as a function of time. And then if we just get that using calculus, then we can multiply it by the mass and we'll have a function for the net force with respect to time. So I'll write it out again. One and 1800ths minus 1 and 1800ths e to the negative 5t. Let's do a little planning. Again, like we did before, I'll go to red just for planning. Kids won't write this when they're doing their solution, likely, because they'll already be doing it in their head. But the time derivative of a constant, well, that would be like this. d dx of x to the n is equal to nx to the n minus 1. And that's like 1 and 1800ths times t to the 0. So take the time derivative of that, it's going to be 0 times 1 and 1800ths 0 times anything is 0. So that's because it's n times all the stuff on the right. So this first part is just going to be 0. That's easy enough. That's really automatic for your kids after their calculus teacher teaches it to them for a little while, or you teach it to them for a little while. And then the derivative of this exponential part, well, that's going to be something like b dx of e to the bx. Well, that is going to equal be to the bx. Easy enough. Okay, so now we know what to do. Our planning is done. Let's go ahead and write out the answer. I've thought about each part of the expression separately, so we can just do it. So the answer for a as a function of t, then, that's going to equal 0 minus -5 times 1 1800 e to the -5t. So that will equal 5.9 e to the -5t. And then f net, or f as a function of time, they just used an f, but I'll put the net on there, must equal the mass, 12 thousandths kilograms, times 5.9 e to the -5t. That, it turns out, is, let me look at my paper version, you get 0.071, 71 thousandths e to the -5t newtons. Okay, another application of the calculus. So that's all the calculus part. That's the 6 points that you get for math. I'll erase that. Well, let's clean this up again. When I glance down on it, I notice how sloppy it is. That was 71 thousandths e to the -5t newtons. Okay, let's go on and let's look at C. It says determine the constant speed of the object. Well, for C1, we need to look at, well, sorry, I forgot to read the first part. The students repeat the experiment with a taller glass cylinder that is filled with the same fluid. The cylinder is tall enough so that the object reaches a constant speed. Determine the constant speed of the object and justify your answer. So we can do that just by looking at our function for v as a function of time. Our function, again, is 1 1800 minus 1 1800 e to the -5t. So we can say, oh, aha, as t goes to infinity, what's going to happen to this function? Well, anything to the negative infinity, -5 times infinity would be negative infinity. Well, as t goes to infinity, e to the -5t, that goes to 0. So the limit of this function as t goes to infinity is just going to be this constant value. So we can just say that v, well, let's say it like this, the limit as t goes to infinity of v as a function of t, that just equals 1 1800 meter a second. Okay, that'll be the constant value that you get for the function. Your justification could just be, you could probably write, as t goes to infinity, the function becomes just the constant value of 1 1800 meters a second. Or you could probably show the math and say this justifies my answer. For C2, it says determine the force exerted by the fluid on the object at this time and justify your answer. Well, C2, if it's reached a constant speed, then we know the forces are balanced. So we have an upward force of the fluid, and that's balanced by the force of gravity. So they must be equivalent to each other. So the force of the fluid must equal mg, and that must equal that 12 grams, 12 thousandths kilograms, times gravitational constant, 9.8 newtons per kilogram, or 118 thousandths newtons. Okay, we've gone through the whole problem. It's a nice problem perhaps for a review. Your students, if you have calculus learners, they're not going to be ready for this for quite a while. You might save it till the second semester, or at least the end of the first semester. If you're teaching the calculus along with the physics, then maybe you could do it sooner. I tend to not do it that way. So I use this as a review question at the end of the year, and then we went over it pretty much in this manner, step by step, and went over the scoring guideline as well. I might post a screencast of the scoring guideline so we can look at the learning objectives and how they match up with the points. Thanks for watching. It's been Mark Reef. Remember, what one fool can learn, another can.